In this video, we're looking at the very last test that we're going to be doing for infinite series, and this is the root test. In the last video that we did, we took a look at the ratio test, and the two are quite similar to each other. Okay, the actual conclusions seem almost identical. The only difference is going to be that the limit we look at is different. So let's sort of get into what the root test is. We'll talk about sort of which series you would think about applying the root test to, and we'll sort of develop some intuition about why it is that the root test works. So similar to the ratio test, we're just taking our series, we're doing a limit, but this time we're doing the limit of the nth root of the absolute value of an. Okay, you'll remember for the ratio test, we were doing an plus 1 over an in absolute value, and that's really the only difference. Right now we're just doing a different limit because the rest of the test is very much the same thing. We are looking at what that limit gives us. Okay, and if that limit gives us a value that's small, if it's less than 1, again, we have convergence. If that limit is large, if it's larger than 1, we're going to have divergence. And again, exactly like the ratio test, if that limit is equal to 1, then the test is going to be inconclusive. The test fails, you go and you try something else. Okay, so what we want to look at now is why the root test works the way that it does. Okay, let's sort of give ourselves some intuition about how it works. The first thing that you want to remember is similar to the ratio test. What did we have as our result for a geometric series? For a geometric series, everything came down to this value of r. And we said that based on the value of r, if the absolute value of r was going to be less than 1, okay, then we're going to have convergence. If it was going to be larger than 1, then we had divergence. And if it was equal to 1, well, for the geometric series, we had that it was also going to be divergent. Okay, but let's just sort of focus on these two possibilities first. Let's just look at what happens if it was less than 1 or larger than 1. Okay, and let's see how that applies to the root test. So for the root test, the idea is this. And again, you need to remember this is not a proof by any means, but this is very much the idea, what is going on behind the scenes in the root test. So if we are doing the limit as n goes to infinity of the nth root of absolute value of n, and we end up getting L, okay, then the idea is that for large values of n, we could say here that these two are going to be approximately the same. Okay, they're going to sort of be very close to each other in value. Okay, this is going to be true for large values of n. And in that way, what we end up getting is that the absolute value of an is going to behave in a similar way to L to the power of n. Okay, for large values of n, we have that our terms, okay, the absolute value of an, are going to behave sort of like L to the n. Okay, and that means that the terms that we're adding up, okay, so remember that our series was the sum of an. Okay, so the terms that we're adding up, they behave like L to the power of n. So our series, an, is going to behave in the same way as something like L to the power of n. And L to the power of n is just exactly a geometric series. Okay, what's the common ratio? Well, the common ratio is L. Okay, now again, this is not a proof, okay, but this is the idea behind the root test. And if our series behaves like a geometric series with a common ratio of L, then it's no doubt why the conclusion works the way that it does. If our common ratio L is less than 1, then our series is convergent. And if it's larger than 1, then it's divergent. Okay, the only thing that's really different here is that what happens if the root test is equal to 1? Okay, well, if the root test is equal to 1, similar to what we did for the ratio test, okay, you can go and you could look at some examples. Okay, just take here even the two examples, 1 over n, do the root test on 1 over n, and do the root test on 1 over n squared. You're going to get the similar problem. You're going to get that one converges and one diverges. Okay, the limits are going to be much more complicated. I'm not going to get into them, but if you end up getting 1 as your limit for the root test, it's inconclusive because you don't know whether it diverges like the harmonic series or whether it converges like 1 over n squared. Okay, but again, that's sort of the only difference really between our conclusion for the root test and our conclusion for the geometric series. Otherwise, we want to sort of think about them in the same way. We want to be doing this nth root, and we want that nth root to be less than 1 for convergence, larger than 1 for divergence. And we really don't want it to be equal to 1. Okay, so now let's go and look at a couple examples of how the root test works. So here we have our two examples, and the first thing that you'll notice is that both of them have these sort of common exponents. Okay, one is to the power of n, one is to the power of 5n, and this is exactly what you're looking for, okay, for the root test. It's a huge sign that you should be considering the root test, because if you take the nth root and you have an nth exponent, then those are going to cancel out very nicely. So it works very efficiently in this situation. So let's sort of set ourselves up here. Let's do the limit of the nth root of the absolute value of an. And you're going to see in a moment exactly why it is that this is related in that way to the geometric series. So the first thing is that we're going to cancel out the nth root with the nth exponent. We don't need the absolute value here. Again, it's part of the test, but for this one, as if n is positive, everything here is positive. So we can drop the absolute value, and if we drop the absolute value, then the nth root cancels with the nth exponent. And we end up getting the limit as n approaches infinity of just 4n plus 3 to the power of 7n plus 2. And this limit, you could do L'Hopital's rule. You could look at the degree. It's degree 1 over degree 1. This limit is going to be 4 over 7, and L'Hopital's rule will get you to the same thing, because the derivative of 4n plus 3 is going to be 4, and the derivative of 7n plus 2 is going to be 7. So this limit exists. It's 4 over 7, and now you remember, okay, which test it is that we're doing. We're doing the root test, which means, similar to the ratio test, we care about what this limit is. Okay, this limit is specifically going to be a number that is less than 1, which means that our series is going to be convergent, and it's going to be convergent by the root test. Okay, and again, let's just sort of take a look back at how we connected the root test to geometric series. Okay, what we're saying when we look at this is that our series, okay, behaves approximately in the same way like the geometric series 4 over 7 to the power of n. Okay, because this term inside, it approaches 4 over 7 as n approaches infinity. Okay, and so for large values of n, that sort of describes the behavior of our series in terms of convergence or divergence. And because it would be a common ratio of 4 over 7 that's less than 1, that means that it's going to be convergent. Okay, so let's get rid of this. That's sort of going on behind the scenes here. But otherwise, the ratio test just gives us right away that our series is convergent. So let's go and take a look at the second one. Here we recognize again we have an exponent of 5 times n, and we can do the root test. So we have limit as n goes to infinity, we take the nth root of 2n over n plus 1, and then here 5n, and this is all in absolute value. So again, we can drop the absolute values, okay, because n is going to be positive here, and everything is going to be positive for these terms. We end up getting that the nth root and the 5n here, they're going to cancel each other out in terms of the n's, and what you end up doing is the limit of 2n over n plus 1 just to the power of 5. Okay, and now as n goes to infinity, what's actually happening? We have 2n over n plus 1. As n goes to infinity, that's going to go 2 to 2. You could use L'Hopital's rule, you could use our shortcut. So this whole thing is just going to give us 2 to the power of 5. We're using here the root test, so we care whether that limit is larger than 1 or less than 1. And in this case, it's larger than 1, which means that therefore, our series is going to be divergent by the root test. Okay, so here we've seen now a couple examples using the root test. really you're using the root test, okay, whenever you have your series AN is actually sort of, of this format. You have some patterned set, you have Bn, and it's raised here to the power of n, or maybe it's raised to the power of 5n, or raised to the power of n squared. Okay, all of those sorts of situations you can think about doing the root test for. So now we have looked at all of the tests, okay, starting with the nth term test, we've done integral test, we've done the two comparison tests, and now the ratio and the root test. So here, the difficulty now is if you are not given the test to use, how do you know which test to use? Okay, and so you have to do some practice, you have to go back. In each of the videos, I've talked about sort of what it is about the series that leads me to try a certain test. In this one, you're looking at those exponents in order to do the root test. For the ratio test, we were looking for combinations of p-series with geometric or factorials, okay, and that led us to do the ratio test in those situations. So go through now, figure out what it is for each test that you're sort of looking at, and again, the best way to make sure that you get comfortable with these is just to practice. The more that you do, the more comfortable you will get, and the faster and more reliably you will be able to answer these.